right, hope you all had a good long weekend. We have this issue still to solve. If you recall, we left ourselves with this. Here is a beta keto ester. It's a bifunctional group. It contains two functionalities. It has a ketone, which is more reactive than the ester. And if I attempt a reduction with a strong reducing agent, then I reduce the ketone to a secondary alcohol, and I reduce the ester through an aldehyde, which we never collect, down to a primary alcohol. If I use a mild reducing agent, then I manage to reduce the ketone, but I don't get to reduce the ester. Okay, so I've got some selectivity here, that if I change the reagents, then I change what gets reacted. But then the question comes, what if I want to keep this part of the molecule intact and only reduce the other part of the molecule? Well, that sounds impossible, because that involves you reacting the least reactive part right here, and then leaving the most reactive part untouched. So we have to come up with a solution. And the solution is to go ahead and react the most reactive part selectively, softly, with something that's reversible. And then go ahead and do a hard reaction on the ester to turn that into an alcohol, and then undo the thing that you started with. So what I need to get from here to here is a reaction that will reversibly tie up the ketone. So I'm going to take the ketone, convert it into something, do the reduction, and then undo my first reaction. This concept is called a protecting group. We're going to tie the most reactive part of the molecule up and then undo it. And if your first reaction is reversible, then you could do some really clever things. Remember this. Ketones, if we react them with alcohols, turn into hemiacetals. And if I react them with two alcohols, then they turn into acetals. So here's a ketone, and if I react that with two alcohols, then I make the acetal. And the acetal and the ketone that it was formed from are reversible. And here's the really good trick. There is something I can do from Thank you. There is something I can do from general chemistry that will help push this reaction to the right. So here's my ketone. I have 2 alcohols on either side of it. I'm going to lose 2 molecules of water and make an acetal. If instead of using 2 separate alcohols, I used 1 molecule that was a diol, then entropy works to my favor. All right. So a ketone plus a couple of alcohols makes an acetal. If instead of using 2 alcohols, I used a diol, and especially if that diol makes a 5-membered ring or a 6-membered ring, nature loves those things, then I start on the left-hand side with something that has 2 molecules as reactants, and on my right-hand side I have something that has 3 molecules as products. That means I've generated more randomness in the universe. So entropically, this reaction is likely to happen. And all I have to do to push back at the end is add lots of water and a little bit of acid. Okay, so here's what I'm going to do. I have 3 scenarios: strong reducing agent, mild reducing agent, and currently impossible. I'm going to take a diol, also known as glycols. This is ethane diol. I'm going to form this kind of intimidating thing right here. But it's just an acetal. If you put your thumb over the offending thing, like we did down here, then it's just a geminal diether. It's not that intimidating. That has reversibly tied up this ketone. That ketone is now not subject to reduction. So I can go ahead and reduce the ester, and I have to use the strong reducing agent. And that's going to put the alcohol here. And then I just hydrolyze off that acetal, lots and lots of water, little bit of acid, and I get my ketone back. Okay? This concept right here is that the acetal is working as a protecting group. it prevents the most reactive part of the molecule from progressing in this reaction. Okay? I wish there was more protecting group chemistry that we could get to in chemistry 2. There is a lot of it. And when it comes to synthesis and design of reactions, it has an active part. But we have to move on. Questions about that? We're basically at this point done with all of the synthesis part of the text. What we're going to move on to now is just biomolecules, descriptive chemistry. Okay. Remaining questions about this? All right, good. Let's move on. This has been up for a couple of days. It's going to be difficult to remove. Ugh. Maybe I just do the easy thing. There you go. It's going to take too much time. All right, let's talk. My head is in the way. Can we see the top of the board now? I'm going to move the camera. All right, carbohydrates. Carbohydrates are sugars. And carbohydrates are moderately simple. They can get deceptively complex, but they tend to follow a predictable pattern. And the carbo in carbohydrate stands for the carbon, and the hydrate means water. So for every number of carbons that we have, Cn, for simple sugars, I'm going to have the same number of water molecules. Which is why things like glucose is C6H12O6. Glucose is easily the most important sugar. If you knew nothing at all about sugar, but you knew a little bit about glucose, that would be a good place to be. That would be a good place to start. Turns out that all sugars end in ose, O-S-E. So if your molecule that you're looking at ends in O-S-E, it is a carbohydrate. It is a sugar. And all sugars are polyhydroxy ketones or aldehydes. And the absolute simplest, easiest sugar that we can look at is a little molecule called glyceraldehyde. And glyceraldehyde has this formula. there's an aldehyde, there's a secondary alcohol, and then there's a primary alcohol. And glyceraldehyde, however, is hiding something from us. Glyceraldehyde has a special, somewhat hidden behavior. What is it about glyceraldehyde that we're going to have to pay attention to? Can anybody see it?
Isn't it combustible? Like flammable?
All sugars burn, but it's not, yeah, I mean, I wouldn't worry about it. Don't worry that you have to lock down the sugar in your pantry. It's not going to, it has a high enough activation energy that it's not going to spontaneously combust. So it's not the combustion. There's something physical in its structure that is very easy to overlook in molecules, but is lurking in this molecule. And it is not at the aldehyde, and it is not at the primary alcohol. It's the secondary alcohol in the middle. Anything special about that secondary alcohol?
Is it chiral?
It is chiral. And it's this secondary alcohol is chiral, and this is the simplest one that we have, and this only has 3 carbons in it. Then glucose, which is an aldehyde at one end and a primary alcohol at the other, and 4 secondary alcohols in the middle. That's going to have a whole bunch of chirality centers. It's going to have 4 chirality centers. So, we should probably redraw our sugars as Fischer projections. And when we do, we always put the carbonyl part at the top. Carbonyls in Fischer projections of sugars go at the top. Primary alcohols go at the bottom. And then the secondary alcohols go in the middle part. And this is new pen. It's really good. Carbon 1, carbon 2, and carbon 3. So in this particular sugar, carbon 2 is chiral. And that gives me this isomer and that isomer, one of which is an R and one of which is an S. One of which is a plus and one of which is a minus. The plus and minus, remember, are the actual physical behavior. Does it rotate light to the right or to the left? If you put a solution of this in a polarimeter, would it bend plane polarized light to the right or to the left? And then R and S, it's just a naming convention. Just a naming convention. That we're going to prioritize these, and we would prioritize an oxygen has a mass of 16, carbons have mass of 12, but this carbon is bonded to oxygen 2 times, so that gets to be priority number 2, and this gets to be priority number 3. 1 to 2 to 3. Is that the R or the S?
S.
Why is it the S?
Because it's going counterclockwise.
Counterclockwise means S. Sinister. And what was the thing about the bond of lowest priority?
It's pointing away.
Yeah, and is it pointing away?
No.
No, so it's not an S, it's a...
R.
Okay. Because the bond of lowest priority is not pointing away from the viewer in this Fischer projection and will not be pointing away from the viewer in any of our other Fischer projections, because we're going to write them all the same way. That is an R. It looks like an S, and therefore this one has to be the S. Okay? R and S. Okay. Bear with. That's the simplest sugar. This is glucose. Am I really going to have to count R or S at 4 different chirality centers? No. No. That part is gluc. Okay. The relationship between where the alcohols are gives us the gluc part. And then I just tag os onto it. So for the sugars, if we had to count the absolute configuration at every carbon, that would be an absurd amount of work for us to do. It would just be too much work. So what we're going to do instead is rely on the relative positions. This way, that way, this way. We're going to rely on the relative positions of the alcohols and then give every sugar its own name. Think for a second of words that you know that end in OSE. Os. Throw some at me. Tell me the names of some molecules that end in os. was a little bit too quiet.
Sucrose?
Sucrose. Sucrose is a disaccharide. It's two little sugars stuck together. The two sugars that are stuck together are glucose and fructose. You may have heard of fructose. It's fruit sugar. Anything else?
Galactose?
Galactose that you'll find in chocolate, because it's not quite as sweet as glucose, is a mono saccharide. It's one small little molecule just like this, and its repeating unit is slightly different. And then you've got lactose. Lactose is a disaccharide. So anything that ends in ose. How about ribose, as in RNA, and in deoxyribonucleic acid, DNA. Ribose is slightly smaller. It's only got 5 carbons in, not the 6. They all have a different repeating pattern, and that makes you switch out the front part of the word. Okay, which is. Go ahead.
What's the difference between sucrose and sucralose?
Sucralose is an artificial sweetener. Have to look up its structure at the end. I think it's got some chlorines replacing hydrogens in the alcohol groups. We can look that up as we get closer to the disaccharides. Remind me later to look that up for you. Some of the artificial sweeteners throw chlorine into the molecule. Chlorine's in group 7, so it does essentially the same kind of chemistry as hydrogen. Makes one bond at a time. But there's not a lot of biological relevance to things that contain chlorine, so it doesn't have its metabolic activity. So, by giving the molecule its own name based on relationship, I solve a problem. The problem is I don't now have to count the R or S for each individual chirality center. And then, typical biologist trying to solve a chemical problem, it generates its own problem. Now I have to memorize the names of every individual sugar. I have to know the difference between ribose and xylose and ribulose and lysose and galactose and lactose and sucrose and fructose and glucose and gulose. Yeah. So everything now has its own name rather than some kind of systematic naming system. What we've saved on one hand, we have to give up with the other. What this does for us is mostly good, but that relationship could go this way. This molecule and that molecule both have the same relationship of alcohol groups. So these both end up being glucoses. Only we count this one. It's really important. When we look at sugars, we read sugars from the bottom up, not from the top down. The bottommost chirality center in a molecule determines which group it belongs to. If the bottommost chirality center has the alcohol to the right-hand side, then that is a D isomer. D for dextro. Dextro being right-handed. If you're ambidextrous, you have two right hands. Or you have two hands that are both as good as right hands. If your bottommost chirality center is to the left, then you are an L sugar, which is levo, L-A-E-V-O. The dumbing down of America is continuing because this combination of vowels, the A-E, has been deemed to be too complicated for you to understand. And so levo has now started to be spelled as L-E-V-O. And with that goes the potential for people to make an uneducated guess at how to pronounce that word. It is not pronounced levo. It is pronounced levo because there is a missing vowel there. It's the same vowel combination as in Julius Caesar, A-E. Okay. So I have left sugars and right sugars. And it turns out that, at least on this planet, all of the sugars with any biological activity at all belong in the D sugar group. So every molecule that you can think of that is a sugar, this is a D, and that is an L. Any molecule can be written either in its D form or its L form. Only the D isomers have biological activity on this planet. Maybe on other planets, the sugars are left-handed. But on this planet, our sugars are right-handed. Okay. One chirality center here in glyceraldehyde generates two isomers, two optical isomers. What if I had two chirality centers? How many isomers would that generate?
Is it 4?
It is 4. What if I had 3 chirality centers? How many isomers would I generate?
6.
It's not 6. It's 8. If I had 4 chirality centers, how many stereoisomers would I generate? 16. So glucose, up on the board here, I'm just removing it so that I can draw it again. This is glucose. I've drawn it in its right hand form. So this is D-glucose. D-glucose has 4 chirality centers at the 4 secondary alcohols at carbons 2, 3, 4, and 5. D-glucose is 6 carbons long with an aldehyde. Glucose is what we would call an aldohexose. Ose, it's a sugar. Hex, it's got 6 carbons. Aldo, it contains an aldehyde. If the top carbon is an aldehyde, remember aldehydes can't be chiral, and the bottom one is a primary alcohol, that leaves me 4 places. 4 chirality centers generates 16 stereoisomers. So if I want to look at glucose in reference to the other sugars in glucose's world, I need to write 15 other structures up on the board, which I'm not going to do. Good news. On this planet, only the D sugars have biological importance. So 4 chirality centers generate 16 isomers, 8 of which are D and 8 are L. And I'm going to ignore the L sugars for right now, until I'm told at some point in the future that L sugars are important and should be revisited. I'm only going to pay attention to the D sugars. Okay? All right, at this point in regular lecture, we would learn how to draw these molecules repeatedly by putting them up on the board. What I'm going to do with you now is share come on, you can do it. Share the lecture notes from previous years. So let me see if I can make that bigger. Oh, I think that only makes it bigger on my end. I don't know that it makes it bigger on your end as well. No, it doesn't look like it does. Okay, hold on. So these are the lecture notes. Jennifer.
On our end, it has the option to zoom in.
Yeah, so you can zoom at your end. I'm going to scribble on this a little bit, but if I zoom on my end, it doesn't automatically zoom at your end as well, is the message right here. Okay, how am I going to do this? I can do this that way. This is for later, and it's a little bit awkward, but here we go. Okay, so on this page, it basically runs through, here are sugars, here's how they exist. They exist in a beautiful little piece of biochemistry where photosynthesis and metabolism are the exact opposite of one another. That's fabulous. Not a single gram of carbon, oxygen or hydrogen goes to waste, and every single joule of energy gets converted from one place to the other. If you take 6 carbon dioxides and 6 waters with photosystem from chlorophyll and some sunlight, there's your external source of energy, then you can combine those carbon dioxides, you can fix those carbon dioxides down into glucose. Plus, as an added bonus, plants give us oxygen. So 6 carbon dioxide, 6 waters makes glucose plus 6 oxygens. And then we breathe the oxygen, we consume the carbohydrate from eating plants or animals that also eat plants, and we turn that glucose plus the oxygen back into carbon dioxide plus water, and then we release the energy. Okay? Fabulous. And there's a good chance you've been lied to. And that's all right, to some extent. Where do you think your caloric intake of carbohydrate goes? What particular body function do you need sugar for? Where does your sugar intake actually go to?
Glycolysis of the citric acid cycle.
Okay. All right. Treat me like a 6-year-old that I don't know what citric acid and glycolysis is, but I know what sugar is. And I know what running around outside is. And I also know what reading a book is.
Sugar makes you go. It gives you energy.
Yeah. That's the big lie. It doesn't. It doesn't. You were probably lied to that you need sugar to make your muscles work so that you can run around and be active. It turns out that for humans, about 70% of the sugar that you consume goes to brain function. 70% of your sugar intake goes to keeping your brain active. If you were a bunny rabbit, maybe sugar gets to have you hopping around in the backyard. But humans, that's not true. If you've ever driven cross country, long stretch, 6, 8, 10 hours at a stretch, you've been sitting on your behind all day. When you get out of the car, you're completely exhausted. Why are you exhausted? You've not done any work at all. Well, you've actively been trying not to die for the past 10 hours. And that consumes a huge amount of sugar. You need sugar for brain function. It's the number one use in humans is not muscles. It is brain function. So this first page runs through how sugars get made. Let's see if I can do this. And then there is a little scheme at the bottom that talks about D's and L's, right-handed sugars and left-handed sugars. Okay, look for that bottommost alcohol group, the one on this particular sketch that is in blue. Look for that to be either on the right hand side and therefore a D sugar, or on the left-hand side, and therefore be an L sugar. And then every different arrangement of alcohol groups gets its own name. Okay, next page. Glucose, C6H12O6, is by far and away the most important sugar. But it shares that formula, C6H12O6, with another very important sugar called fructose. It turns out that in metabolism, most sugars are funneled through glucose. So if you were to consume something that wasn't glucose, you have enzymes in your body that will massage those sugars until they become glucose, and then you'll metabolize them. Okay. Or some approximation of that. Glucose has 4 chirality centers. That generates 16 stereoisomers. 8 are Ds and 8 are Ls. If we take that leap and say, I'm only going to pay attention to the D sugars, not the L sugars, then that gives us a series of 8 aldohexoses. And that's what you can see at the top of this page. There are 8 sugars, and they're called allose, maltose, glucose, mannose, gulose, idose, galactose, and talose. And let me see if I can do this. They're all written in a way that the aldehyde is at the top and that the primary alcohol is at the bottom. And then I have a series of alcohols. And of course, at the bottommost secondary alcohol is always on the right, because these are the D sugars. Now, someone is going to make you memorize all of these. It's not me, but somebody is, if they haven't already, some of you may have already had to memorize these. Someone's going to make you memorize them, because biologists love memorizing stuff. From a chemistry point of view, there's a couple of things in here that we can key onto and then just know the relationship. So if I look at allose, this is allose. Right now I'm putting a blue, is that showing up? Yeah. I just looped all of the alcohols in allose. I put them all in a blue loop. And this is relatively, I can write on this screen, hold on. Allose is going to be easy to remember because the prefix for allose is ALL, and all of our alcohols are on the right hand side. So you'll see underneath allose, underneath D-allose, there is a little asterisk. This one says memorize me. And then the other one that you have to know is glucose. And glucose was that rearrangement. But if you knew allose, we can get to glucose, because I can tell you that glucose is just allose, except the configuration at carbon number 3 is reversed. Okay? I don't know if I can undo that. Oh, wrong one. Oh, that's awkward. All right, so from allose, if I remember that one thing, then let me see if I can do this. There you go. With all the alcohols being on one side, I can use this as a starting point. And if you look back at the exams from previous years, it says questions like, D-altrose is an aldohexose. It differs from allose at carbon 2. Draw altrose as a Fischer projection, and then it asks you to draw it in a couple of different forms as well. So, underneath all of those structures for allose, altrose, glucose, mannose, gulose, idose, and galactose, there's some blue text. And it says that glucose, D-glucose, and L-glucose, they're enantiomers. They are mirror images of one another. That's the left and right, where every single alcohol group is the mirror image of the other one. But because we don't really need to look at the L sugars, we're not going to see enantiomers on this list of 8 molecules that we've got. That's something else instead. So if I take any 2 of these sugars, I should be able to know what their relationship is. So the blue text says allose and talose. That's the first one and the 8th one. Allose has 4 chirality centers. Talose has 4 chirality centers. These 2 molecules differ at multiple chirality centers. They are diastereoisomers. We introduced diastereoisomers very early on in Chemistry 1, and we said if you had 2 chirality centers and one of them was different, that was a diastereoisomer. Here we've got 4 chirality centers. Some of them are different. Now there's a special case of diastereoisomers that if only one of your molecules, if only one of the chirality centers is different, then that diastereoisomer now becomes something called an epimer. And we can see that altrose, second on the list, and allose, first on the list, differ only at carbon number 2. Oops. Come on. Trying to... Here. Oh, come on, you can do it. Carbon number 2 in altrose is different than carbon number 2 in allose, but everything else is the same. Therefore, allose and altrose are C2 epimers. Glucose and allose are C3 epimers. Glucose and mannose are C2 epimers. So if you learn glucose and you have to know the shape of glucose, and you know allose, and allose is so easy to remember because all of the alcohols are all on the same side, then simply being told that one of the other sugars is an epimer of the other will let you know everything on this list. That's the way of getting around this. Okay, now further down, and this will be the last thing, below the blue text at the bottom of the page, there's another set of diagrams. And fructose is highlighted at the bottom of that page. Let me just get to it. this that I'm putting in a little blue box right now. Ugly, ugly. That's fructose. Fructose is C6H12O6 as well as glucose is, but fructose is a ketohexose. It has a ketone at the top, not an aldehyde, which means it only has the possibility of having 3 chirality centers and belongs to a different set. It has stereoisomers that are called psychose, sorbose, and tagatose. When we come back on Wednesday, we're going to redraw all of these molecules in 3-dimensional shapes that are either 5-membered rings or 6-membered rings, because we're going to turn the ketones and the alcohols, the aldehydes and the alcohols, into hemiacetals. Aldehyde plus alcohol makes hemiacetal. Okay. This is a skill. We'll learn it on Wednesday. Watch the video before you come to class Wednesday. Watch the video from last year. Read the notes. And that's what we'll be up to. Okay. I'll see you all on Wednesday. Yep.
So I know that we have a take-home test.
Oh yeah, I forgot to mention that. Yeah, go ahead.
We have a final too as well, correct?
Yeah, so your final, I'm going to just write you a quiz. I'm going to write you a quiz with some problem-solving exercises in that quiz, and that will be your final.
Okay, so it'll be like a quiz on like Blackboard?
It's going to be on Blackboard. Yeah.
Okay.
And it'll be open. Your final's supposed to be Tuesday, I think. It's Tuesday or Wednesday?
I'm not sure.
Yeah, I think it's Tuesday. And I'll have it opened for like most of the day.
Okay, gotcha.
Mm-hmm.
Thank you.
Okay. Yeah, I forgot to mention that.